Now we can discuss on sp hybridization. As the name indicates, sp hybridization means intermixing of s orbital and p orbital results hybrid orbitals, and that hybrid orbitals, when it is mixing with the half-filled atomic orbitals of any atom, it will be results the sp hybridization and forms the covalent bond. We can discuss with examples this hybridization. At the same time, this sp means, you know that out of 100, s character it should be having, s orbital character it is having 50% and p is having 50% its character. Okay, so here just to start with explanation with the help of BeCl2 example. You all well familiar with this compound. Beryllium, the atomic number it is equal to 4, so electronic configuration is 2,2. You can write the electronic configuration subshell wise, so you can write it 1s2 2s2. In the case of hybridization, we are considering only the valence number of electrons. So here this is the valence shell, only 2 electrons. So here we can represent beryllium in ground state here like this, 2s only, there is not 2p orbitals. So here in the 2s, how many electrons? Here 2 electrons. So just represent like this. Here you want to be check with that. Here 2 chlorine atoms. Chlorine, you know that 1s2, 17 is the atomic number, 1s2, 2s2, 2p6, 3s2, 3p5 is the way of writing the electronic configuration. So here in the outermost shell, when we are considering 3s and 3p only, so 3s you know that 2 electrons and p having 5. So first you know that rules and all, you know that first filling, afterwards only pairing. So here one is half filled one. So the p orbital one, it is half filled. So likewise 2 chlorine atoms here. So when the 2 half filled chlorine it's there, surely you need 2 half filled orbitals in the beryllium atom. Then only the hybridization possibility or covalent bond formation. So what we need in the next step? So chlorine it is having 2 half-filled orbitals, one from one chlorine and other chlorine also having the same half-filled orbital. So 2 half-filled orbital it's there in the chlorine, so automatically beryllium also need 2 half-filled orbitals. For making the half-filled orbitals in beryllium, we need to be excite the beryllium in the next step. So what is the next step after 2s? Surely the next coming group it will be 2s, next coming group it will be 2p. Okay, so what we will do at the time of excitation, one of the electron from 2s it will be going to the next shell. So here one from this 2s it will be going to the next orbital, 2p orbital. Okay, likewise one more half-filled orbital it is created here. Clear? Then what is the next procedure in the hybridization? After getting 2 half-filled orbitals, next step is hybridization. Hybridization means intermixing of these 2s and 2p orbitals. So one orbital from 2s and one orbital from 2p. So 2 of this orbital forms, we already studied that in the characteristic, how many number of atomic orbitals are intermixing, that much the same number of hybridized orbitals it is forming. So that means here 2 orbital it is mixing, so 2 hybridized orbitals it is forming. Then which is the hybridized orbital's name? Can you say now? It is easy. Which all orbitals joined? The name of that one, nothing more. So here s and p it is joined, so 2 sp hybridized orbitals it is forming. Okay, these 2 of these sp hybridized orbital, both of them having the same character. Then this, after this 2 sp hybridized orbital, each sp hybrid orbital combines with p orbital of chlorine. Each chlorine. one sp hybridized orbital combined with one chlorine and another sp hybrid orbital combines with another chlorine. So automatically overlapping of atomic orbitals happened and forms the covalent bond formation. Next step is how we can do the picture of the sp hybrid orbitals of this BeCl2. As I already told, whatever the hybridization, if it is sp2 or sp3, hybrid orbital we have to be mentioned like this: big lobe and small lobe. Sometime for our listeners we will use big lobe only. So here BeCl2, you know that 2 sp hybrid orbitals. So around beryllium, either you can draw like this, big one and small one, but for our listeners we will not draw this central atom, only hybrid orbitals, it's enough. So this is one of the hybrid orbital and this is another hybrid orbital. Why we are drawing like this? Because BeCl2, there is a 2 sp hybrid orbital it is forming. So if there is a 2 electron pair, when it comes according to VSEPR theory, we studied that the structure it is linear. So here that same method we are using. If there is a 2 is the hybrid orbital, if it is forming, linear is the structure. When linear is the structure, bond angle should be 180 degree. The same thing here. So that's why I mentioned this hybrid orbitals like this. This is one sp hybrid orbital and this is the another sp hybrid orbital. Then what is the next stage? Each hybrid orbital it is combining with a chlorine's p orbital, because chlorine is half filled one. So I will use this. Each sp hybrid orbital it is combined with p orbital of chlorine. Okay, so this is the hybridized portion and this also. So that one I can draw like this. This is the combined portion. This is the p orbital of chlorine. So this is the picture of hybrid orbitals. Then the structure, you know that BeCl2 is Be, Cl, Cl. Bond angle is 180 degree. Why, how it is coming like this? Here like this. This is straight line, no? So this is the center. Here beryllium joining with the chlorine. Likewise, if you want, you can remember. Here you can see that end to end overlap or head on overlapping it is happening. So this joining bond it is 2 sigma bonds. So here itself, when you are looking one bond and the another bond, these both are sigma bonds. We will discuss on some other examples of sp3, sp2 and sp hybridization. So for that I took first is ethane molecule. That molecule maybe you are knowing in organic chemistry, last year you familiar with this compound ethane. So structure also you know that CH3 CH3. Okay, so you knows all the things, the structure, everything, you knows it well before going to be study about this hybridization. But how this structure it comes, that we can discuss now with the help of this hybridization. Okay, here you knows there is a 2 carbon CH3 CH3. This is the simplest form. So here 2 carbon is here, 1 carbon and 2 carbon. Yes, so each carbon we have to be considered here in this type of hybridization. So carbon, as you know, the atomic number is 6, 1s2, 2s2, 2p2 is the electronic configuration. So outermost electronic configuration we can write like this: 1, 1, 1. Okay. This much only. But here you need to be think one way. Here we can discuss like this. This carbon, it is joining with 1, 2, 3, 4. It want to be joined with 4 other elements. 3 of them with hydrogen and 1 with other carbon. So it needs 4 half-filled orbitals. Clear, no? So how many number of bonds we need? It needs to be make that much half-filled orbitals. It's needed in the excited state. Here only you know that there is a 2 half-filled orbitals. So we can write like this. So in the next stage, when we are trying to be write an excited state, what will be happen? One of this electron, it will be going to the next shell, vacant shell. So what will be happening here? Here already 2 it's there. One of this one, it is going to be this place. So 2s and 2p. So you know that 3 half-filled orbitals and one more, it's ready here. 3 for this hydrogen. Hydrogen, as you know, its electronic configuration is 1s1. This one also 1s1. This one also 1s1. So 1 half-filled orbital in each. And this one we need to be joined with other carbon. For that we made the 4 half-filled orbitals with the help of excitation. So this is first carbon's case. The next carbon, when we are doing the same situation, it will be arises. Because if you consider this is C1, this is C2, this C2 carbon also, it is having the same situation. It is bonded with 1, 2, 3 and with this carbon. So 4, it is also being bonded. Okay, so with the help of one carbon, we can explain everything. The same situation for the next carbon also in this. So we have to be, as per our theory, the hybridization, just intermix this atomic orbitals. Due to this intermixing of this atomic orbitals, it will be resulting with what a type of hybridization it is. Intermixing of atomic orbitals here. Atomic orbital here in the sense 2s and 2p orbitals only. 1 2s and 3 2p. So totally you know that how much? 4. 1 plus 3 4. Then how many number of s it is here? S. And p, how many of them having half-filled? 3. 4 sp3 hybrid orbital of each carbon here. So here we can draw here the hybrid orbitals now. Each carbon, each one having 4 sp3 hybrid orbitals. So I told you how can we draw the hybrid orbital. How likewise. So we can draw like this. 4 sp3 hybrid orbitals we need to be make now. So here one with the you knows that 1 sp3 hybrid orbital with the next carbon that you knows. Then already I told you the member's name, that means central atom's name, it's not to be considered. That's not a necessary thing while drawing the picture. So here this is first carbons. For hybrid orbitals I am going to be draw now. This is another hybrid orbital and this is another hybrid orbital, and for our reasoners I am going to be draw like this. Okay, this is the next way. So 4 lobes, equal lobes, it is good. So this is 1 sp3 hybrid orbital of carbon. This is 1 sp3 hybrid orbital of carbon, and this is 1 sp3 hybrid orbital of carbon, and this is 1 sp3 hybrid orbital of carbon. So 4 sp3 hybrid orbitals of the carbon, it is ready for one carbon. Okay, next carbon hybrid orbitals we can draw now. So what is the next carbon's case? Next carbon also I told that the same situation it will be coming. So for sp3 hybrid orbital it will be having. So what is the next thing? This carbon, just imagine this is the carbon's carbon. So what is the next thing? Draw the 4 hybrid orbitals. For your easy understanding only I used with different colors. So here 1, then okay 3 it is ready, and 1 it is making with this bond. Okay, this is 1 sp3 of carbon, and this is 1 sp3 of next carbon, and this is also 1 sp3 of the next carbon. This is 1 sp3 of the next carbon. So in this picture you can notice that one carbon it is joining with other carbon. That is why this particular portion we, okay, this is C end-on overlap or head-on overlap. So this is a sigma bond joining. Okay, clear now because of this carbons joining. Okay, then what is the next thing? So one half-filled orbital, 1 sp3 orbital from each it is joined. Then here in each carbon 3 more it is remaining. So you know that in the case of C2H6, 2C's problem we completed, then H6 it is remaining, or otherwise when you look you can see that 1 2 3. So each carbon want to be made with the bonding of 1s orbital of the hydrogen. So hydrogen's 1s orbital means you know that it is having the spherical shape. So each one, this one, all it is half-filled one now. So each half-filled sp3 hybrid orbital, it is joining with 1s orbital of the hydrogen. Why it is circle shape? You understood now, because of the 1s orbital having the spherical shape. So each carbon, it is having the bonding with the 3 hydrogens. So understood. Then here also, okay, clear? This is hydrogen, this is hydrogen, this is hydrogen, and you can see that one portion it is common here. This is the joining portion. So here also end-on overlap. So this is also sigma bond. Here also you can sigma bond. Here also you can sigma bond. Here also you can sigma bond. Here also sigma bond. Okay, sigma bond formation it is happening here because only single bonds here. Here you know that there is a single bond formation. Here single bond formation. Here single bond formation. Single bond formation. Single bond formation. Single bond. Single bond. So everywhere the single bond you can see here. That is why we are saying that only sigma bond is here in this particular compound. So we can conclude the structure of C2H6 ethane molecule like this. Both of the carbon atoms CH3, in this both of the carbon atoms it is sp3 hybridized. So out of 4 sp3 hybrid orbitals in each carbon, one of sp3 hybrid orbital it is making overlap with the other carbon, similar orbital of the other carbon atom to form CC sigma bond. They are axially overlapping or end-on overlap or head-on overlap. It is happening here. Other 3 hybrid orbitals, this one, this one, this one, each carbon that overlaps axially with 1s orbital of the hydrogen atoms to form CH sigma bond. Okay, so the structure it will be like this: C single bond C, that is this bond, and this carbon it is joining with one hydrogen, another hydrogen, and another hydrogen. So that will be structure like this. And this carbon, one bond, another bond with the 3 hydrogens. Okay, so this is the structure.